What I'd like to do today is show you some methods to measure the time constant of a first order RC circuit. Just for a quick review, there's a first order low pass filter circuit, and over here we can see the RC connected up with the function generator and the circuit. Now I've got the oscilloscope in the acquire mode on average, and I think I've got it set to about 4 or 8, and I'm measuring a few things. First thing I'm measuring is at the bottom, and it's the rise time, and that's how long it takes to go from 10% to 90% of the final value. Now, how long should you make the period of your square wave to measure your time constant, right? You do the step response, and then you'd find 5 tau, right? Well, if you're looking for 5 tau, then the period should be 10 tau. However, your circuit might vary due to variances in the R and the C, so you probably want to go for 6 tau for the pulse width and 12 tau for the period, so that it can get all the way up to where it needs to go. Now, I calculated in this circuit that the period should be about a millisecond, and if we zoom in here, we can see that it's measuring a rise time of about 202 microseconds, but I'm not actually giving it enough time to get to its final value, and I'm going to start increasing the period, and you can see that the rise time now from 202 goes to about 210, and I have to reset the statistics to see that. Alright, so it's right there at the bottom, and it's about 208. Alright, if I go the opposite way, well, notice it's not going all the way up, and it's going towards the center, and it's actually acting like a pulse width modulated filter, and the rise time is about 40. So you have to go long enough. Now, if you go too long and you have to auto scale, you lose some accuracy in the measurement. All right. So now that we've got a rise time, we can come over here. All right. So I measured 208 microseconds, and we can convert, take the rise time and multiply that by 0.455 to get tau. There's a derivation there that you can look up. So we get about 94.6 microseconds, and then if we calculate the cutoff frequency, we get 1.682 kilohertz. So I'm going to actually do 1.62 kilohertz and go to a sine wave, and I'm just trying to see if I can get a better scale. Alright, so now I'm over here, got it zoomed it in a little bit, and now the ratio I'm getting minus 3 dB at about 44 degrees, so it's not exactly right. So I'm just changing my function generator to what worked before I started this video, reset the statistics, and now the mean is about 3.06. That's kind of as close as I can get, and the phase is minus 44. Now, you might recall that the phase should be minus 45 when you're at the 3 dB point. Essentially, the the ratio or the gain is a more accurate measure, or it's easier to measure that than the phase. So really, you just know that the phase is negative, and it's heading in the, you could say, the right direction. So what we measured from the, we predicted that we should have a cutoff frequency of 1.682, but when we measured it, it was 1.699, and that is pretty much the measurement technique. And I'm just going to go back to show some things. Sorry, so you might notice, like, where is this error coming from? And you'll notice that the yellow, the input, isn't in a perfect square wave. And what's going on is that there is a 50 ohm series resistance in the function generator, and the capacitor has a parasitic inductor in it. And so it doesn't look exactly like it. And if I take it off of, put it onto normal mode, you can almost see if it goes up and comes down, it almost looks like the input is a notch filter. So the input isn't really a step. So maybe that's what's causing the issue. When we measure with the sine wave, it's a lot more, it's closer to just one frequency rather than a step response, which might be a little bit harder. And if we come over here and compare that to our Bode plots generated with Python, the one on the left, I just going around the cutoff frequency, and you can see the phase goes from about 0 to 90, and the magnitude looks like a first order. However, when you bump up the frequency to 10 megahertz, you start to see the magnitude creep back up and the phase creep back up. And that is due to the fact that it isn't exactly a first order circuit. In fact, the parasitic resistance and the parasitic inductance in here gives it 2 zeros, and if you do an LT spice plot of that, you can see the phase creep back up and the magnitude start to creep back up. Even though this isn't a perfect RC filter, it actually works as a pulse width modulated filter quite well, and in another video I can show you that it gives 5.1 effective bits.